In this video, we'll create a dynamic interaction system in UEFN using Verse. Players will highlight objects in their line of sight, and we'll set up foundational mechanics to manage item interactions seamlessly. First, we'll create an empty Verse file and name it Custom Interaction Device. Let's start by creating the item base class. This will be the foundation for all interactive items in our system. In item base, we define three main properties. Item prop. This property is of type creative prop and lets us assign a visual prop for each item. Item type. This uses our item type enum, where we can choose an item type, such as cube, sphere, donut, or cone. 𝐂𝐚 pickup. This is a logic flag, set to false by default, which controls whether the item can be picked up by the player. Each property is marked @editable, so we can easily customize these items directly in the editor. Building this item base class first sets up a solid structure for adding more types of interactive items. Now, let's add an editable array called interactable items to the custom interaction device class. This array holds multiple item-based objects that players can interact with, making it easy to manage items within one device. Here, you can see how our interactable items array looks in the editor after building the code. It's now ready for us to add and customize different items directly within the editor. Speaking of items, I created an item blueprint and some basic items for this tutorial using Unreal's modeling tools. These items will serve as examples for testing our interaction system as we move forward. I dropped the created item blueprints into the level and named them for clarity, like item 1 cube and so on. Then I added these items to the interactable items array under the item prop property. I also set their item type, for example, cube for the cube items, sphere for the sphere items, and the can pickup property to true since these items are pickable. After this, I created a basic outline material, but you can use any outline material of your choice. Here's how I did it. I first created a folder called Material in the content browser, which we will reference in our verse code later. Then I right-clicked in the content browser and selected Material, naming it mOutline. In the material settings, I set the blend mode to masked and the shading mode to unlit. I created a vec4 node, converted it to a parameter node, and named it color. I attached its RGB pin to the emission input. Next, I added a two-sided sign node, connected a 1- node to invert the two-sided sign, and linked it to the opacity mask. I then created a vertex normal WS node, created a scalar parameter named scale, and multiplied it with the vertex normal WS node. The output was connected to the world position offset. Finally, I applied and saved the material. That's it. You now have an outline material that you can customize as you like. Now, I duplicated item 1 cube, parented it to the original, and renamed it to item 1 cube outline. I then assigned the outline material we just created to this duplicate. Scaled it up by 1.05, and set it to be hidden in-game by default. This duplicated object will serve as the outline for the original cube item. Repeat this process for all the other items in the level, following the same steps to set up outline objects for each one. Now, I'm going to create a cinematic sequence to control the object outlines. I'll guide you through the process step by step. First, create a new level sequence and name it 𝐿𝐿 Highlight. Select all the item outline props in the scene, then drag and drop them into the sequencer. With all items still selected, click the plus button, choose Actor Hidden in Game to control their visibility. Next, switch the timeline from frames to time by clicking on the FPS button and selecting Show Time as Seconds. Here's the main part. We'll set up visibility keyframes for each item to create the highlight effect. Starting with item 1, keyframe its visibility so that at 0.0s it's off, at 1.0s it's on, and then at around 1.3s or 1.5s, back to off. For item 2, do the same steps, but shift the keyframes by 2.0 seconds. So at 2.0s, it's off, 3.0s, it's on, and 3.5s, it's off again. Repeat this process for each item, adjusting the timing to create a staggered highlight effect. A helpful shortcut is to copy the keyframes from the previous item and paste them onto the new one, then snap them to their respective times. This sequence will create a custom highlight effect for a specific player without affecting others in the game. I added 2 editable properties to the item base class, outline off time and outline on time. After building the verse code, I adjusted their values to match the timing we set in the sequencer. For example, for item 1, outline off time is set to 0.0 and outline on time to 1.0. This configuration aligns the visibility of each item's outline with the cinematic sequence so they appear and disappear at the correct times. I've added a cinematic device for player 1 in the level and attached the level sequence we created to the sequence property. I set the visibility to instigator only, level sequence actor always relevant to false, and finish compilation state override to force keep state. With this setup, the cinematic device will only play for the specific player it's assigned to, rather than for everyone in the game. This way, The item highlight effect will be visible only to the player who is close to the item, ensuring that other players don't see it. Now let's create a basic GameManager class to handle multiplayer functionality. This class will serve as the central hub for managing game-related features across multiple players, ensuring that interactions and mechanics function seamlessly in a multiplayer environment. Next, a separate verse file will be created to define all the gameplay tags. This ensures better organization and makes it easier to manage and reference the tags throughout the project. In this file, 3 gameplay tags will be created. 1. Custom devices. This tag will act as a parent to manage all custom device-related tags under one unified category. 2. Game Manager. This tag will be used to reference the Game Manager class in other verse files, making it easier to access and interact with. 3. Player Spawner. This tag will be used to identify and manage all player spawners placed in the level. These tags help organize and streamline interactions within the game logic. This code sets up player spawners by finding all devices tagged with player spawners. For each spawner, it checks if it's a valid player spawner device and subscribes the onPlayer spawned function to its spawned event. The onPlayer spawned function triggers whenever a player spawns. It ensures the spawned entity is a player and then initializes that player using the initPlayer function. This setup ensures that all players spawning in the game are properly handled and initialized. To manage players and their associated controllers, a player controllers map was introduced in the GameManager class. This map stores a relationship between each player and their respective player controller. A basic player controller class was also created, which includes a reference to the player it is assigned to. This class can later be expanded to handle player-specific logic, making it easier to manage and organize functionality for each player. Here, the initPlayer function ensures that every player gets their own player controller. It first checks if the player already has a controller in the player controllers map. If not, it creates a new player controller instance for that player and stores it in the map. This setup guarantees that each player is properly managed and initialized with a unique controller. Next, I created the Per-Player Devices class to manage devices specific to each player. In this class, we define an editable property called Item Highlight Cinematic, which will handle the cinematic sequence device for item highlighting. Then, I added 2 key editable arrays in the Game Manager. The Per-Player Devices array holds instances of the Per-Player Devices class for each player, and the All Players array keeps track of all active players in the game. In the initPlayer function, I updated it to add the player to the all players array. This ensures that we have a list of every player who joins the game. I also call the init function in the player.controller class to initialize the player's specific data and default settings. With this setup, we're now ready to manage cinematic sequences for each player individually and keep track of all players in the game. I added a variable player devices in the player_controller class, which holds an instance of the per_player_devices class. This will allow us to manage devices specific to each player, such as their item highlight cinematic sequence. Next, we need a way to access our GameManager class within the player controller. This connection will allow the player controller to interact with the GameManager for various functionalities, such as retrieving shared game settings or triggering game-wide events. Let's work on setting up this connection to ensure seamless communication between these components. Previously, the usual approach to access the GameManager was by creating a global function getGameManager. This function used getCreativeObjectsWithTag to fetch the creative device from the level tagged with GameManager. However, after a recent update in Verse, the getCreativeObjectsWithTag function has been replaced with findCreativeObjectsWithTag. The limitation is that findCreativeObjectsWithTag can only be used within creative device classes. To adapt to this change, I modified the getGameManager function to work specifically within creative device classes. The updated function is now in creative device, getGameManager. Here's how it works. It takes a creative device as input and uses findCreativeObjectsWithTag to locate devices tagged with custom devices GameManager. The function then iterates through the found devices, checking if each can be cast to the GameManager class. If a valid instance of GameManager is found, it is stored in an optional variable and returned. This adjustment ensures compatibility with the new Verse update while maintaining the functionality of accessing the GameManager class. The function was adapted to return the player controller for a specific player by introducing the parameter player. It locates the GameManager using the findCreativeObjectsWithTag method, then accesses the player controller's map from the GameManager. This map is checked for the relevant player to find the associated player controller. If the player controller exists, it is stored in an optional variable and returned. This adjustment ensures the function works seamlessly with the updated Verse API while providing a clear and focused way to retrieve the player controller for any given player. To access the GameManager from the player controller class, a reference to a creative device is required, since findCreativeObjectsWithTag can only be used with creative device classes. Typically, in this situation, I would create an empty MISC creative device class, or a similar placeholder, and pass its reference to non-creative device classes, such as player controller. In this tutorial, though, we won't be accessing multiple classes, so I am directly providing the reference to the GameManager class in the player controller class. This simplifies the example, but is not the most scalable approach. However, if you plan on accessing multiple classes with findCreativeObjectsWithTag in non-creative device classes, it's better to use the approach where you provide a reference to a single creative device class, like the MISC class, during construction. This way, you can use tags to retrieve any creative device class that you've placed in the level dynamically, instead of manually providing references for each class. This method ensures more flexibility and scalability for your future needs. In the init function of the player controller, I added a step to dynamically assign devices to the player. Here's the explanation. After retrieving the Game Manager's list of devices for all players, we use the player's index in the All Players list to find the devices that are assigned to them. By checking the last player's index, GameManager.AllPlayers.length1, we ensure that the newly added player gets the correct devices. Once we retrieve the player's devices, we assign them to the Player Devices variable within the Player Score controller. This way, each player will automatically receive their personalized devices, such as item highlights or other custom features, without having to manually assign them each time a player joins. This ensures that player controllers are properly initialized with their respective devices and are ready to handle player-specific interactions. Don't forget to add the correct gameplay tags to the player spawners and Game Manager devices. Now that we've wrapped up the multiplayer functionality, let's refocus on the main element of the game, the interaction device. Let's break this down step by step. Get closest object function. This function starts an infinite loop with a 0.1 second pause in each iteration to reduce system load while continuously checking for the closest object. First, it validates the agent and retrieves its associated player, player controller, and fort character. These components are essential for interacting with the game world. Find closest object function. This function is responsible for finding the nearest interactable item to the player. It takes the player's current location as input and initializes a variable to track the closest object within a default radius of 3 meters. It iterates through all items in the interactable items list. For each item, it calculates the distance between the player's current location and the item's position. The distance is converted from centimeters to meters to maintain consistency. If an item's distance is less than the current minimum distance, the function updates the minimum distance and sets the closest object to this item. After iterating through all items, it returns the nearest object, if any. In the getClosestObject function, we enhance object detection by using a projected location rather than the player's exact position. To achieve this, we calculate a current location based on the player's forward view. First, we retrieve the player's current position using fortCharacter.getTransform translation and their view rotation with fortCharacter.getViewRotation. Using the view rotation, we derive the forward direction through getLocalForward. Next, we adjust the player's location by projecting it 150 units forward along the calculated forward vector. This adjusted position, stored in current location, represents the area in front of the player's view. Finally, we pass current location to the Find Closest Object function. This ensures that the search focuses on objects directly in the player's line of sight, improving the accuracy and responsiveness of the interaction system. We'll draw a debug sphere at current location to visually verify its position to 150 units in front of the player. This helps ensure the interaction range and direction are correct during testing. I'm extending the Get Closest Object function to track and manage the previously highlighted item. Here's the process. First, I added a variable, maybe old closest object, to store a reference to the last closest object. Next, after finding the closest object, I added a check to ensure we only handle new objects when maybe old closest object is empty or null. Finally, if a new object is found, I trigger the item highlight cinematic and update maybe old closest object to reflect the newly detected closest object. This ensures smooth transitions and avoids unnecessary retriggering of the highlight cinematic. Let's set up the Play Item Height Light cinematic function. This function manages the item highlight cinematic for a player. It retrieves the player and their associated player controller to access the cinematic sequence device. If the outline should be shown, the function sets the playback time to the item's outline on time, briefly plays the cinematic, and pauses it to display the effect. Conversely, if the outline should be hidden, it adjusts the playback to the outline off time and follows a similar play-pause process. Returning to the getClosestObject function. If no closest object is found, it checks whether there was a previously identified closest object using maybe_old_closest_object. If an old closest object exists, the item highlight cinematic is played to hide the outline, effectively removing the highlight from the previously identified object. The maybe_old_closest_object is then reset to false, clearing the reference to the old object. If find closest object identifies a new closest object and an old object already exists, it first checks if the old closest object is the same as the new closest object. If they are the same, no action is needed, and this ensures that unnecessary changes or cinematics are avoided. If the new object differs from the old closest object, it hides the highlight for the old object by playing the cinematic to disable its outline. Afterward, the old closest object is cleared by resetting maybe old closest object to false, preparing for the new closest object to be set. To access this script anywhere, we will do the exact same steps as we did with the Game Manager. I will not be commenting in this stem as it takes time in editing. Now that we have access to the interaction device class, we can use it to perform the getClosestObject function. In the initPlayer function inside the Game Manager, using getInteractionDevice, we obtain a reference to the interaction device placed in the level. After that, we spawn a new thread with the spawn command to execute the getClosestObject function for the player, running it on a separate thread for each spawned player. This ensures that each player's closest object is calculated in parallel, without blocking the rest of the game. This approach allows us to efficiently check and process the closest object for each player without causing delays in the game. To test the code, we need to ensure that the verse tags are correctly added to both the interaction device and the Game Manager devices. Also, ensure that all exposed properties for both devices are filled out. This ensures that the game can reference the correct devices during runtime. Let's test what we've built so far. First, enable the Verse Debug Draw setting by navigating to Island Settings, Debug, and toggling Verse Debug Draw. This will allow us to see the debug sphere drawn at the player's look-at location. As you can see, items are now getting highlighted based on the direction our player is looking. If you'd like access to the full code, you can support me on Patreon. The link is in the description below. That's it for this video. In the next part, we'll dive into implementing the object pickup and drop mechanics.